Last time I discussed the transition to revolutionary science and what revolutionary science was all about. The transition to revolutionary science happens when significant anomalies turn up, and significant anomalies are problems which, contrary to the expectations that you have in normal science, cannot be solved. And after a while, even when the best people have tried for a long time, then people get the suspicion that it's not their own inability why they can't solve these problems, but that the framework, the guiding framework of normal science, is just unable to do so, such that they think that they have to give up this form of normal science that they practiced so far and have to find a new framework in which normal science is possible again. And that means then that we come into a new practice of science, namely one in which you cannot rely on the traditional way of doing science, but you're trying out new ways and try to invent new frameworks in order to re-establish the practice of normal science, which is extremely successful. So these significant anomalies, this was an insignificant anomaly, but it was an anomaly anyway. It's contrary to what I expected. And here we go again. That the significant anomalies then lead to this practice of extraordinary or revolutionary science in which you try to find a new framework. This is a practice that resembles in some respects pre-normal science because you have again schools that compete with each other, but the main difference is that in revolutionary science you have a history of normal science, and that means that, for instance, you know exactly where the points of difficulty are, namely the significant anomalies. Whereas in normal science, you don't have this sort of structure. In pre-normal science, you don't have this sort of structuring because people are insecure what the real problems are, and depends on which school you are. But in revolutionary science, there is a very clear focus of attention, namely the significant anomalies. In addition, everyone knows that the new theory that you're looking for must preserve a lot of the old achievements. Otherwise, the older theory would still be better in spite of the anomalies, because there are many solved problems, and the new theory one is looking for must be able to preserve these achievements, or reproduce them at least. Okay, so we have this sort of revolutionary science that then, in the case of success, leads to a new form of normal science by having, very similar to pre-normal science, by having achievements or presenting achievements that solve the significant problems, so most of them, such that people believe that they have now a new framework in which normal science is possible. I then started to discuss this transition to this new phase of normal science. It is called a scientific revolution, and it's these cornerstones of scientific development, like the chemical revolution, of which you probably don't know that much, in the beginning of the 19th century, or of course the big revolutions in the 20th century about special relativity and general relativity, and also of course the big revolution happening after Bohr's atomic model with the quantum theory from 95, where we have the transition really from classical physics to quantum physics. So these are the revolutions, and they have a number of very interesting features, and the most interesting feature is called incommensurability, and that describes the relationship, or first denotes, because it's not a description yet, it denotes the relationship between the old phase of normal science and the new phase of normal science. It's called incommensurable. Incommensurability is a term coming from mathematics, and it concerns the relationship between the side of a square and its diagonal, and there is no common measure for these two lengths, as you probably know from mathematics. Now, incommensurability is an interesting relationship because it not only applies to mathematics, but in this metaphorical way it also applies here to the transitions to normal science, to the new phase of normal science. But I will tell you at the end, once I have developed that for science, that it's a much more general relationship, and a relationship that may concern some of you directly, because it also concerns the development, the relationship between different cultures. So when you in your home country think of your grandparents, who may be very traditional people in your home country, and you try to tell them what you do when you do Western science, and you may encounter difficulties, then I'm going to explain you what the source of these difficulties are. It's probably incommensurability, but I'll come back to that. Let's first go then to the scientific case in which we have a fairly good transparency. We can fairly well understand what's happening there. And there are three aspects to incommensurability, three senses in which the new tradition of normal science lacks a common measure with the old tradition of normal science. And I developed the first one of these senses in the last session, namely regarding concepts. The common measure meaning that is lacking between the new phase and the old phase of normal science, meaning that in the new phase new concepts are introduced in order to describe the area of research, but these new concepts cannot be expressed in terms of the old concepts and vice versa. I gave you some examples, and that's, I mean, the very meaning of a revolution, that you create something very new, such that it is a real break to the past. And the break concerns, in this particular aspect of revolutions, the nature of the new concepts that are introduced. You cannot understand the new concepts in terms of the old concepts. Or you may put that in another way and say you cannot translate the new concepts in the old concepts. You cannot express the new concepts by the old concept. That's just not possible. But you have to learn something new. You have to understand something of the new framework, of the new theory, and you must forget, in some sense, parts of what you've learned from the old theory. That's the idea of a revolution, and that's therefore something, well, which is associated with the revolutionary, in general, revolutionary character of science, that scientists come up with completely new ideas. And it's difficult to understand them, and one of the difficulties, of course, is highlighted by this incommensurability, because you cannot, to someone who knows the old theory, explain the new theory in terms of the old theory, such that on the basis of the old theory, he or she can understand the new theory. But it's such that you have to say, look, forget about parts of your old theory. I'm going to explain to you somehow differently what the new theory means, possibly or most probably by showing you the paradigms, the new paradigmatic solutions of the theory. And once you understand how they work, then you start to understand how the new theory works, but it's no way of trying to understand the new theory in terms of the old theory, by expressing it with the words that are used in the old theory. That's the revolutionary part here, and that's that part of the lack of a common measure that characterizes incommensurability. That far I got in the last session. I know that this is a little tricky and difficult to understand. Are there any questions so far? If that's not the case, then I continue here. It's not that difficult. You understand what I'm talking about? Partly? Yes? Roughly? Okay, it's not completely implausible? Good. All right, so I told you about the wave function in quantum mechanics, the concept of an ether in field theory. These are examples of things that cannot be understood by the older or by the newer theory in comparison, because they are just very new. The wave function in quantum mechanics is something which is, well, waves are known in classical physics, but the wave function in quantum mechanics is really something very different from anything that's in classical physics. Now, let me now go to the next point, and the next point may be a very surprising one. For most of you, I guess, because usually what we think is that the data we are measuring are something like a fixed point in the following sense, that once you've measured certain data, then you can use them in order to compare different hypotheses. I mean, that's probably what you do, some of you at least, do in their master's thesis. You measure certain data, and the data are somehow fixed, and then you use the data, for instance, to test a hypothesis or to confirm a hypothesis, but the data is something on which you rely, right? This is the same idea, by the way, basically, that we found in inductivism, right? The fundamental idea in inductivism was, let us start with theory-free data. Theory-free means then we can rely on them. They are safe ground, right? We work from there. And that's something that I told you already in inductivism. In deductivism, it was clear that this idea had to be given up because data aren't, unfortunately, that solid, absolutely solid, that you can absolutely 100% rely on them, because the data contain theoretical elements, and the theoretical elements may be wrong. And therefore, there may be there is the possibility that you have give up or change data because of these theoretical elements. Now, in this particular case here, in paradigm theory, this element of the theory-ladenness of data, as it is sometimes called, the theory elements within the data, that leads also to some incommensurability, in the sense that you cannot use exactly the same set of data in order to evaluate different candidates now for the new theory. And that may be a little amazing, but here is the argument that the choice of data and the methods of their measurement may be influenced by the theories which make use of them. Right? This is not something completely new to you, that the theories may influence data, but here it is even, well, in a sense, stronger, because I tell you more about this, not only qualitatively, that, yeah, they may influence the data, fine, but it may be such that the choice of data you think that are relevant, that depends on the theories you're looking at, right? So the data are not something, again, independent of theory, but they are dependent on theory. And if you have two theories to compare with each other, then in the light of one theory you think these data are relevant, and in the light of the other theory you don't agree about the relevance of these data. Okay? That sounds very funny, because we usually, probably from your training in science, as far as you got a training in science, which you all have, I guess, that we usually assume, oh, the safe side of science is the data, but that is not the case. But I give you an example to make this plausible, and the example is something you may not be familiar with, and I have to tell you first the relevant physics. The relevant physics is this, that at the end of the 19th century, or rather the last, well, in the 1860s as far as I remember, people had measured the planetary motions of the planets around the sun to a very great accuracy. And the following effect was discovered with Mercury, the most inner planet. Here you have the sun, and you have Mercury, and I'm exaggerating now. Mercury runs around the sun on an ellipse. Mercury. All right, it's an ellipse. Like the Earth around the sun, it's not a circle, it's an ellipse. But it's not that bad as this one, but that doesn't make a difference. Now the point is that Mercury, in fact, does not really run on an ellipse around the sun, but it's a more complicated thing. It's a sort of spiral. And you can describe the spiral in the following sense, that you say this ellipse itself is moving. Right? The ellipse of Mercury around the sun itself is turning, such that the real motion, now I'm exaggerating again, looks rather something like that. It goes this circle, and then it goes this circle, and then it goes this ellipse, and so on. I'm exaggerating here massively, right, in the speed. So very slowly this ellipse is turning itself. So Mercury doesn't really run the same ellipse every time, but the next time it runs a slightly displaced ellipse, and then another slightly displaced ellipse, and so on. That was discovered. And the figures here is 570, the total 570 arc minutes per 100 years. Okay? That's very little. You know, 1 minute, seconds, I'm sorry, it's seconds. So you know, 1 degree is 1/306th of the full circle. And then 1 degree has 60 minutes, right? And every minute has 60 seconds. So 1 degree is 3,600 seconds. So this is something like 1/6 of a degree. Right? That's very, very little. 1/6 of a degree in 100 years. All right? So the ellipse has turned around 360 degrees in 6 times 360 is roughly, say, 2,000. And then we have wait a minute, what did I calculate just? Yeah, well, it's extremely slow. I can't calculate it in my head right now. Okay, that's the point. It's very slow, right? 1/6. So in something like 2,000 years, if I get that, no, much more, 100 years. Well, in a very long time at least, the whole thing moves around. It's a very small number. It's a very small angle, but people could measure it. Now the point is that by classical physics, by just normal classical physics, you could account for most of these 570 arc seconds. You could calculate that. For instance, the movement of Mercury is influenced by Jupiter. Jupiter is the most massive planet. Jupiter exerts gravitational effects on Mercury, and one of the effects is that the ellipse on which Mercury travels, that ellipse is moving. Also, we have the movement of the Sun. The Sun itself is rotating roughly 30 days per one revolution in 30 days, and that also contributes. So the point is that people could, out of these 570 arc seconds per 100 years, they could account for most of that, right? They could calculate that from classical physics. And what was left was a small amount of 42 arc seconds that could not be accounted for. That's roughly 6% of the value. So what was the reaction of scientists at that time? That was known from the end of the 19th century. People knew that, right? They said, okay, the total effect is 570 arc seconds. We can account for almost all of it apart from 42 arc seconds. And that's, as I said, is something like 6% of that. Is that possible? Well, a little more, right? 7% of that value. So what was the reaction of the classical physicists who worked in astronomy? They said, well, we are on the right track. We can calculate 93%. There are 7% missing. We don't know why. We don't know why. There must be a mistake somewhere. There must be some additional effect we have not taken into account. Yeah, bad luck, but no catastrophe, no panic, right? Once you have an effect and you can calculate 93% of it, then you are very confident that you can calculate the rest as well, right? People said, so we can calculate, perhaps Saturn has a stronger influence, or Mars, or whatever, right? There may be many, many possible effects why this is so. People even invented an additional planet. People said it may be an additional planet in here somewhere, you know, that may account for this strange movement of Mercury. They didn't know. But nobody panicked or was insecure about classical physics. Now you see, This value then of precisely 42 arc seconds was not taken seriously, right? If it were 45 arc seconds, or if it were 40 arc seconds, or 38, was irrelevant, right? You see the point? Because it was the rest of something you could calculate, and there was some rest, a small rest, less than 10%, which you could not calculate, and the precise value of 42 seconds was just not interesting. Quite clearly, it's a rest unaccounted. You didn't know why, and whether that rest was 42 or 43 or 45 or 38 was just unimportant. You knew something was missing, you didn't know what was missing, and you said, we are certainly on the right track because we can account for 570 arc seconds, and there is some rest, and the precise value of this rest is unimportant, right? It's a datum, you measure that, said, okay, we are that far, but we don't know about the 42 arc seconds. So this is a datum, it was measured, but nobody took the exact value of 42 seconds very seriously. This would have been interesting if you have another method to calculate it, and then whether you find this difference of 42 arc seconds or you don't find it. Now the point is, that changed it completely when general relativity was invented by Einstein. General relativity is a theory of gravitation that is the successor theory after Newton's theory of gravitation. And in Einstein's theory, Einstein was able to calculate exactly these 42 seconds, right? In Einstein's theory, he could exactly calculate that the missing part of that movement of Mercury was an effect coming from general relativity theory, and was, in the eyes of the general theory of relativity, a contribution to the movement of Mercury's orbit that was impossible to get from classical physics, because it was a specific effect from general relativity. So for Einstein, this particular value of 42 arc seconds was extremely important, really extremely important, because that was the exact number that Einstein could calculate with his theory, right? And that then finally convinced people because of that exact number that he could calculate. So from Einstein's point of view, the exact number of 42 arc seconds was extremely important. It was an extremely important datum. Whereas from the point of view of classical physics, it was not an important number. It was just something missing, something of the order of 7%. And people didn't care whether that was exactly 42 arc seconds or 38 or whatever. They simply knew we can't account for it, we don't know where it comes from, but it's probably no catastrophe because it's just a small part of what we can calculate, right? A small part of the whole effect that we can calculate and account for, and this small rest, we don't know where it comes from. So you see that, and if someone had said, say, someone had recalculated that stuff, and then the result would have been, say, 38 arc seconds, people would have said, okay, so 38 arc seconds. It's not important. It's a small rest. We don't know where it comes from, but the exact number does not really matter from their point of view. But from the point of view of general relativity, this number was very important, especially because general relativity could exactly account for it, right? If general relativity would have come up, say, with 38 arc seconds, they would also have said, well, this number is not very important. There's something unknown in here. But as soon as classical physics plus general relativity was able to calculate exactly these 570 arc seconds, and that the rest was accounted for by general relativity, then this number became important in the light of that theory. So you see that in a situation where you don't really know what's going on, the precise numbers sometimes are not very important because you don't know what's going on, and therefore you can't say how good this number, how important this number is, because you don't know where it arises from. And then you may say, once we understand the effect, perhaps we have to recalculate and the number will change, right? But as soon as you have a theory that tells you exactly this number, then you know it's an important number, right? It's just the prediction of your theory. And that is one of these examples where you see that slightly different sets of data are seen as relevant. Of course, both theories say, yes, altogether we have an empirical effect here, 570 arc seconds per 100 years. It's an important effect, we have to understand it. Fine, wonderful. And then you start working. And then you know that your result is not very precise. You have an error of 7%. And the exact amount of the error is not significant unless you understand exactly what the source of the error is. And then it becomes a significant number, because then it's an indicator that you have really identified the source of the error. And then you say, okay, that's marvelous, because then now we know that we really understand the phenomenon. There is a classical contribution to the phenomenon of 570 arc seconds, a classical contribution meaning to be explained by classical physics. But there is an additional contribution to these 570 arc seconds, and that is coming from general relativity. And that is because Mercury is fairly close to the Sun, and the gravitational field of the Sun is fairly strong in comparison to the other planet. And it is strong enough such that effects from general relativity can be felt. General relativity disagrees with classical Newton's gravity. The stronger the field is, the stronger the gravitational field, the stronger you feel that general relativity is the correct theory to describe what is going on. Okay, is that an example you could somehow follow, the physics as well? Right? It's a normal situation that you have in all science, that once you have something that is not accounted for, say you measure something and then you expect you have an accuracy of say 2%, then, and that means you have an error bar of 2%, then the exact value within these 2% is just unimportant. You simply know my measurement won't be more precise, and you don't want to know, or usually you don't want to know what the precise reasons are why you have exactly these 2%, unless you can improve your measurement and you're interested in an improvement. Then you're interested in it, but as long as you know, okay, these 2% are good enough for what I want to do, then you're not interested in the precise causes that lead to 1.3% in one case or 0.5%. It's just unimportant. It's unimportant data. But in light of a different theory, these data may become very important. And that is one of the reasons why slightly different sets of data may be seen as relevant. And that again means incommensurability in the sense there is no common measure. In the following sense, that you don't have a fixed set of data with fixed relevance that is the same relevance for both theories. Right? That is just not the case, because it depends from which theory you look at the data. And for one theory, data may be relevant, and from another theory, another theory's point of view, they may be irrelevant. Okay, that's the second aspect of incommensurability. It's the data that have not the same relevance for both theories. And finally, there's also something a little disturbing, perhaps at first sight at least, that is that the scientific values you are using in order to evaluate the theory, in order to say which theory is better, that the scientific values you are using in the evaluation, they may depend on the theories in question, which is a very bad feedback loop, right? You want to have the values in order to evaluate theories, and then it turns out that the values are dependent on the theories. So they are not objective in a sense, you know. They are dependent on which theory you evaluate, but that may happen. It's very unpleasant, but it may happen. And the example, this may be extremely disturbing. I mean, what's the idea of the values? Well, the idea of the values is to evaluate different candidates and then to show which one is the best one. But if the values themselves are influenced by the theories, they're not independent of the theories, right? How can they do their job? And the values, I told you, are these scientific values: the accuracy of theories, the fruitfulness, their problem-solving potential, their consistency, and so on. They are supposed, the arbiters, the referees, that say, this is a good theory, this one is a little better, and that's the very best one. right? And the referee must be independent of the things he or she is going to referee. So there is this funny situation that the values themselves are somehow influenced by the theories, and that I give you an example, and again it concerns the transition between classical physics and, in this particular case, quantum physics, which happened, as I said, in the 1920s of the last century. And the problem there is that in classical physics for something like 300 years, everyone believed that fundamental theories must be deterministic theories. Deterministic theories are theories that don't involve probabilities, right? No probability. Everything is determined, right? This is what classical physics says. Once you know the state of a universe at one particular point, you can in principle calculate it for the rest of all times. That means deterministic. It's fully determined what's going to happen in the future. So the belief from the 17th century on until the beginning of the 20th century was that a fundamental theory of physics must be deterministic. The background assumption was the universe works roughly like a clockwork, like a mechanism, right? A mechanical clock is completely deterministic. You know, you set it and then it works and works and works and works. And you can predict it precisely, right? There's no randomness or probability involved. It's just like a clockwork. And the basic idea in classical physics was the whole universe is a clockwork. If the universe is a clockwork, the fundamental theories describing the universe must be deterministic theories, right? Because the thing itself is determined in its development. So if you want to have a good theory, the theory itself must also be deterministic, namely then describing this deterministic process. So in 1925 or a little later, 1926 or 7, people realized that the new quantum mechanics that they had devised, that this new quantum mechanics was a theory that involved some indeterminism. It was not a deterministic theory. Okay? So the problem was the following. You had to make a decision between classical theories, which are deterministic, and indeterministic theories. From the experience with your deterministic theories, people had the idea that we have a value, namely the value of deterministic fundamental theories, and saying a good fundamental theory must be deterministic. If you use that value and look at quantum mechanics, you say quantum mechanics is a bad theory, right? If you come from classical physics, you say, well, that's a bad theory because it's not fully deterministic, right? But when you come from quantum mechanics, you say the basic idea of classical physics that the universe is a deterministic mechanism is false. It isn't, right? From this point of view, you say, no, I don't have the value that fundamental theories must be deterministic. Quantum mechanics tells us otherwise, right? So the value you are using in order to determine which one is the better fundamental theory depends on the theories. It's not independent, right? The value you have developed, that deterministic theories are highly valued in classical physics. If you apply this value, then quantum physics is out. And if you step back a little, then you realize, well, that's pure dogmatism, right? You have classical physics, you derive the value of deterministic theories, and then you value everything else in light of these values, which you have to derive from classical physics. So you're not really open for quantum mechanics, which is not a fully deterministic theory. So we have the problem here that in these revolutions, the situation may happen that the values you are used to using in evaluating theories, that they are themselves dependent on the theories, and you must give them up somehow. And the question is why? Why should you give them up, right? Why is it? Well, in this particular case, it happened that there were according to other values, the new indeterministic, partly indeterministic quantum mechanics was extremely strong, namely problem-solving capacity. It could solve problems the classical theories could not solve. And because of that value, problem-solving activities, people after a while accepted the fact that they said, well, it seems to be that determinism as a value of theories is just not as high as problem-solving activities. So people had to, evaluate their values, which is, again, an activity on another level. That they were forced to, and that was a painful process, as a matter of fact. And in the beginning, Einstein, for instance, the same Einstein from general relativity, refused to accept quantum mechanics. And he said, God does not throw dices, dices and getting numbers between 1 and 6. And quantum indeterminism is something like throwing dices. And Einstein said, no, I don't believe that. I think the universe is a deterministic system and is not some intrinsic randomness, and he couldn't accept it, right? Because he used the value that he derived from classical physics, and he was convinced that these are the right values. So the situation may become very tricky, as it did in the 20th century in that particular case, that the values you are using are not really completely unbiased, but they are also influenced by the theories themselves, right? Like the data. The relevance of the data depends on the theory from whose viewpoint you look at the data. And the same is here. The values themselves are somehow, or can be somehow, dependent on the theories, and then they lose their complete neutrality. And then you have to play around with the values, and that means you are lacking a common measure how to evaluate the theories. Namely, that would be a fixed set of values from which you look at the theories and then evaluate them. Same with the data, you are lacking a fixed set of data which are then relevant for the evaluation of the theories. So what is happening here in these scientific revolutions is somehow that you're losing your absolute neutral yardsticks by which to evaluate the theories. And that is exactly incommensurability. And that makes, therefore, the evaluation of competing theories during a scientific revolution more difficult than one usually imagines, because usually one thinks, well, there are data, and when we evaluate the theories with the data, we know what a good theory is. And then we evaluate the theories according to these values. We have a common measure, namely values and data, right? And incommensurability says, no, if you look close enough, that's just not true. Because a revolution is something, a scientific revolution, may be something so deep that it even affects the data, and it even affects the value you are commonly using to evaluate theories. And that makes scientific development much more complicated than was thought before, and this is one of the great, I think, virtues and achievements of paradigm theory, of namely making people aware how complicated these processes are that happen in especially scientific revolutions.
Professor?
Yeah.
I don't seem to get this point. Are you saying that even before you start the application of this data set to the theory, to test the hypothesis, in a way they are theory leading? It beats my...
Well, just take the examples. I mean, it's just that, as I said, take which one? You have difficulties with the data, that the data...
Yeah, the data is before you start the application of that data to the hypothesis.
Yeah.
They are already influenced.
They are influenced, yes. Yeah. For instance, I mean, you measure, if you take especially these 42 arc seconds, the 42 per century, this is not directly measured, right? These 42 arc seconds that are relevant then for general relativity are not directly measured. What is directly measured is the 470 arc seconds. That is something you can measure, right? And then you start using theories, namely Newtonian gravitational theory. And then you calculate, then you start calculating. You calculate the influence of the sun. There's also a geometrical effect coming from Earth movement. the influence of the Sun, the influence of Jupiter, and this geometrical effect. You use the theory.
No, I mean before you start using the theory itself.
Before you start using the theory, you have to measure these 570 arc seconds. That's a measured thing. Of course, you need a theory of your measuring instruments. This is also not, you don't look there and see, oh, 570 arc seconds per century. It's a very complicated measurement, of course, in which many theories are already involved in the measuring processes, right? You must evaluate your telescopes, you must evaluate your instruments to measure a certain angle, and so on and so forth, right? You have time measurement, a very complicated time measurement, but this one is a fairly, well, comparatively directly measured number, 570 arc seconds per century, right? That is measured, right? Other theories do play a role here. But the next step is when you account for that, when you say, why is it that Mercury moves, the Mercury's ellipse moves in this way? Then you start calculating by means of theory, right? You say, what's the influence of Jupiter? Jupiter sits down here somewhat, has a gravitational field, influences that, and then you get a certain amount by Jupiter, all right? You say, okay, say 50%, I don't know the numbers here. And then you say, okay, the Sun is rotating, and that changes something. And then you calculate only on the basis of the theory, right? Of course, you have to measure the mass of Jupiter. You can't measure directly the mass of Jupiter, but you use Newtonian theory again. You calculate the mass of Jupiter by the frequency, by the diameter of the orbit, and the frequency, then you can calculate the mass, right? It's not directly measured. You use Newtonian theory already. So anyway, so you calculate, then you only calculate, right? The influence of Jupiter, the influence of the Sun, the rotation of the Sun, and this geometrical influence. That's calculated. And then you get a rest, and the rest is 42 seconds. This is not directly measured, but it's derived from this value plus lots of theory, and then you have this number. And what you believe is this is a number that is not accounted for, right? It's part of this movement. So in a sense, it's of course a measured number, but a measured number that has a lot of theory inbuilt. It's not directly measured such that you take a telescope, look out there, look for 5 seconds, and then you have measured 42 arc seconds. No way! It's a very complicated thing, but still you think this is something in principle measured, right? This is a datum, right? And now the point is, how seriously do you take the exact number here of 42? How seriously do you take it? Well, you know, when you come from Newtonian physics, you know that something is not right? 7%. And you don't know where it comes from. You have no idea where it comes from. So you don't even know whether this number is correctly calculated. You don't know that. Because, as I said, that's the rest once you have calculated Jupiter's influence, the Sun influence, and the geometry, right? And you know something is wrong, but you don't know where something is wrong. So you don't even trust this number very strongly. You simply know, look, I don't get, in the end, these 570 arc seconds. But you don't know where the mistake is, you know, where the error is, what went wrong. You don't know that. And therefore, you don't trust this particular number, not very specifically. Because you simply know, look, my calculations are good to roughly 7%. And you don't know more. And once you simply know, well, my mistake is something, my error is something like 7%, you don't even know whether it's only 3%. You just know this is unaccounted for, and you don't know the source, right? This is unaccounted for. And once you don't know the source, you must also, you say, well, do I have Jupiter's influence really right? I don't know. Do I have the Sun's influence really right? Is there something missing that I haven't accounted at all? I don't know, right? Just the fact that this is different, that this is the rest here, tells you that you are not in command or in full command of the situation, that something is wrong, right? You don't know what is wrong. And therefore you don't trust this number really very strongly. You can't. You don't know. You simply say, look, I know something is wrong, and what I so far see is that the difference is 42 arc seconds. But that's certainly not a number you wouldn't trust very strongly, because you simply know something is wrong, right? And because it's wrong, you can't trust what you calculated fully. You just say something is missing, and I don't know what is missing. But the point is completely different when you now start from a completely different theory, namely from general relativity. And general relativity, without taking into account the rest of it, but really purely theoretically, calculates you that the number, the missing, or what is this, the effect deriving from general relativity in contrast to Newtonian physics, that this is exactly 42 seconds. That's a precise prediction of the theory itself. And then you say, look, this is exactly what my theory, my general relativity says, and then this number becomes extremely relevant. Because just imagine it would have been 38 arc seconds here, or say 59, and general relativity calculates 42, then people would say, so, what to do with it? It could be general relativity, but perhaps something else. Perhaps general relativity is not right. People didn't know whether general relativity was the right theory, right, at that particular point. That was calculated in 1916. General relativity was invented in 1915, and people didn't know. I mean, it was a theory, you know, a successor for Newton's gravitation, but people didn't know whether it's the right theory. So they didn't know. So just imagine it would have been, this value would have been different, say 37, and general relativity calculates 42. People would have said, yeah, that could be a coincidence. Pure luck, right? It's not the right number. Perhaps, yeah. Who knows, right? And nobody would, the situation would still have been open, right? Because nobody can trust this exact figure unless you know what's going on. But as soon as you know that general relativity, who could do other things as well, can calculate exactly this missing value, then you think, now we do understand the situation fully, right? And then the number becomes extremely important, right? It's a complicated story. It's good that you asked me again, because it's really a question, as you see, of judgment, right? You have this number, and then the question is, shall I trust this number? Right? That's the question. And there's no pure methodology how you can say, yes, it's clear that you can trust it, or that it's clear that you can't trust it. It's a question of judgment. You have a difficult situation. You know, you have this situation, 570 arc seconds. You can calculate most of it, 93%, which gives you the confidence, should be okay in principle. Something is missing. You know that from hundreds of years that you can never calculate fully precisely, or almost never. And there's always something missing because you have approximations and the measurements are not precise and whatnot, right? You know that. And 7% is such that people said, yeah, we don't know, but, you know, we are on the right track. We can calculate 93% of the effect. Damn it, we should get the last 7% as well when we refine the measurement or refine the calculation or do a little trickling and wiggling, and then we'll get it in the end. So people weren't really in panic. They said, yeah, 7% is missing. That's a nuisance. Of course, it would be better to have only 1% missing, but we have 7%. Yeah, bad luck, damn it. But it's no sign that something is fundamentally wrong. Right? It's just no sign. If classical physics would have said, say, if classical had said, there is impossible that this ellipse moves in a circle. It's impossible. It must be fixed according to classical physics. Then people would have said, of course, there must be something wrong with classical physics because it's really moving. 570 arc seconds per 100 years. It's very, very little, but it's moving. And if classical physics is absolutely unable to account for that, then the theory must be wrong. There must be something deeply wrong, right? But that wasn't the case. It was able, 93% of the effect, to explain, look, these are very, very small things, right? This is, as I said, it's the sixth of an arc in 100 years. Now, let's say a sixth of an arc, so it's in 600 years. It's one degree in 600 years times 360 times 6, so it's something like 2,000 years, right? It moves around in, is it 2,000 or 20,000? I don't know, 20,000 rather. So in 20,000 years, the ellipse moves once around full circle. In 20,000 years, it's a very long time. You measure perhaps in 2 years or something, you measure that, and then you come up with this number, right? So it's very small numbers, and it's very delicate. It's very delicate measurements, it's very delicate calculations, because this is perturbation theory that you have to use to influence. Look, it's not only Jupiter, there's also Saturn and the other planets, and their influence is much smaller, so people usually said it's Jupiter mainly because it's most massive, and the Sun, of course, because it's so close. And who knows what's going on there? Perhaps there is some gas in between Mercury and the Sun that has some effect, you know? We don't know. People didn't know so much. So there are so many different sources that you couldn't really trust this figure, that you couldn't. And therefore people said, yeah, it's something not so important, but the number becomes extremely important, this precise number, once general relativity predicts it. Right? Then you say, wow, that's significant. That's not an accident, right? That exactly this number is predicted. And then the number becomes extremely important. Okay, does this clarify the confusion? Right? This is, you're absolutely correct with your question, because it is a little complicated, and especially since you do not know so much about the physics, but it's very important, I think, to understand that, because this is much more sophisticated and complicated than the normal stories you hear about science. Right? The normal standard stories, yeah, you measure something and test the hypothesis and blah, blah, blah. You know, real science is much more complicated. And incommensurability is one of these aspects that has been a topic for discussion for the last 50 years, because it's fairly complicated. You have to fairly well understand particular situations like this one in order to grasp what's going on here with incommensurability. And the point is, that explains then, as I'm going to tell you after the break, perhaps I should say that right now, yes, that incommensurability does not make theory comparison impossible. I mean, although you don't have this fixed yardstick how to measure, namely data or values or something, you don't have them, but it makes it much more difficult than it is commonly assumed. Usually people think in the more simplified pictures of science that you know, in principle, doing this theory comparison, you just look which theory is better with regard to the data, and here you go, and the one that's better with respect to the data will win. It's much more complicated. Okay, I'll continue after the break. Let's make an 8-minute break, and then I'll continue.